Polynomial theory is a beautiful body of work that began with Descartes in 1637, with his observation that if you look at polynomials with very simple structure, their roots have a very simple structure as well. And in particular, he observed that polynomials in one variable with exactly t monomial terms have no more than t minus 1 positive roots. This blossomed further, some centuries later, into similar results for systems of equations, and in fact you can extend them to analytic functions of a certain kind with parametrized complexity. You can go in a different direction though. Arithmetic polynomial theory seeks to understand varieties from a quantitative point of view and an algorithmic point of view via the evaluation complexity of the defining equations. So this could mean a number of monomial terms, or it could mean the hardness of evaluating the individual polynomials in terms of circuit complexity. So an example of a result from arithmetic polynomial theory would be something, say, over a finite field. And one result would be, say, most univariate polynomials having 4 terms exactly, having on the order of p to the 2/3 roots in fp. So this result was derived around 2000. I'll give you the reference. But the interesting thing is it was one of the first steps towards proving the randomness for Diffie-Hellman. So this is a particular distribution having to do with a particular cryptographic protocol. And certainly the question of randomness is not settled yet, but it was a very important step done by these authors, Canetti, Friedlander, Konyagan, Lehman and Larson, and Sparlinski. And there are results over QP. So this is what I'm focusing on. The p-adic rationals, when you have one polynomial, one variable t terms, it turns out that the number of roots is just on the order of pt squared. And this is a beautiful result that was initiated by Hendrik Leinster in 1997 and later improved by Avendano and Crick in 2011. And what's another result of this kind? Well, that's a bound of the number of roots. You can actually talk about the complexity of detecting roots. And that turns out to be NP hard. So relative to a particular notion of size, taking into account how many monomial terms you have, this problem actually is NP hard. And this is derived some years ago, jointly with Martin Avendano, Ashraf Ibrahim, myself, and Corbin Rusik around 2012. So the focus for today, though, is like, okay, you can bound the number of roots nicely. Detecting roots is hard, but what about solving? Solving seems to be difficult now. But what if you limit yourself? So say to a constant number of terms, say like 3. So 2 is sort of known classically, but 3 seems to be the next open question. And what about 4? And just to look further ahead, speedups enable deeper algorithms, more complicated algorithms for more complicated problems to go farther. So for instance, if you think about, say, p-adic integration approaches towards trying to count rational points on algebraic curves, there's some very heavy-duty p-adic computations, and it would be nice to speed those up. And so if you understand the basics better, then you can actually speed up much more complicated computations. But this is very long-term. So going on to the main theorem, let's consider a trinomial f, a polynomial with exactly 3 terms, and let's say it has degree d, and the coefficients are between, well, they're within plus minus 1 up to plus minus h for some integer h, and consider any prime p. And here's a little notion we're going to need. If you take a rational number, non-zero, we say that it has most significant digit 1 if and only if it's of the form p to the j plus something on the order of the higher order for some j. So in other words, evaluation is j for some j, and the coefficient in front of the p to the j is just a 1. And this is a nice analog. You can think of it as an analog of being a positive real number. Okay? Or if you're thinking in the complex plane, there's different directions you can go in, there's different phases. You can think of the first digit as being, the most significant digit as being an analog of the phase. Okay, so their main theorem is the following. The deterministic time, cubic in the prime, and 7th degree in log dh, you can find succinct approximates of small height to all the roots over the p-adic rationals. Now, what I mean by succinct approximate, I simply mean a rational number with a small numerator and denominator that will converge really, really quickly, doubly exponentially fast, via Newton iteration. Okay? So this result is in a significant improvement because pretty much all other algorithms over the p-adics have complexity polynomial in d, not log d. The dependence on p is a problem, and this is actually something rather difficult to improve upon. There's unsolved number theory problems that you'd have to solve before trying to significantly improve this, but nevertheless you can make some speedups. You can, for instance, speed up significantly, maybe drop an order of p if you're only looking for roots with most significant digit 1. Okay, that's one possible speedup, and there's others that we talk about in the paper. Final note that succinct approximates need not exist for tetranomials. So we actually have explicit families of examples where the roots become too close, and it's simply not possible to approximate them efficiently in the sense that we're doing for 3 terms. So there's a definite boundary for the deterministic complexity, and therefore, if you want to speed up faster, randomization is going to be your friend. And working average case is also going to be very, very useful. Okay, so as an example, let's observe that 229 is a prime. This number here, 229 to the 228, is rather large, has 539 decimal digits. Let's consider this trinomial, which is a non-trivial one. It has a rather large constant term, around 539 digits or more. This one has about as many digits. That's the x coefficient. And the degree, you see, has about 539 digits. So what do we do for this guy? Well, if you want to look for its rational roots, a p-adic rational roots, you could start by looking for its roots over the finite field with 229 elements. And if you do that, you can try even brute force search, since the prime is fixed for the moment. And you'll find that the only roots for the trinomial are 0, which is a non-degenerate root, and 1, which is a degenerate root. And you can think of this as the first digit, or the most significant digit, for the roots over 229. Okay, so now we've got to find more digits. So the question is, how far do you have to go out before you can separate the roots? And we cover this in our paper. Via our estimates and employing earlier work of Hendrik Lenstra and Kun YUYU, in particular his p-adic analog of Baker's theorem on linear forms and logarithms, we see that working with 233 digits is enough. So if you work modulo this power of 229, that's enough to encode all the roots of your trinomial in Q229. And in fact, we can get this. So you have a root evaluation 228 plus higher order stuff, and 2 other roots evaluation 0 plus higher order stuff, and you can distinguish them all. And in fact, you get more, you get an approximate. You get rational numbers that approximate and converge very quickly. The residual error of each of these decays at a rate of this, so doubly exponential in n, after n iterations of Newton's method. And that is all I wanted to say for today. So I thank you for listening. And if you want more information, please come to my webpage. Thank you very much.